Sourav Chatterjee is now going to give his part 3 of his introduction to Gauss theory for probabilists.
Okay, so I have a bit more to cover than the previous two lectures, so I'll go a little faster. So today we are going to discuss, as I said, there is very little known about 3 and higher dimensions. So one of the things that's known are these master loop equations. And this, I think originally this was discovered by Makienko and Migdal in 1979. Okay, and these are also known as the Makienko-Migdal equations. So what they do is that they represent the expectation of a Wilson loop variable in a lattice gauge theory as a polynomial in several other Wilson loop variables. So this works in any dimension. Supposed to work in any dimension, and it's supposed to be kind of a large n feature. So as the group dimension of the group becomes large, as you have SUN or UN theory for large n, and this derivation was not fully rigorous. So it involved this unproved factorization ansatz, which assumed that the expected value of a product of Wilson loop variables approximately factorized into a product of expectations for large n. So that was one of the assumptions that was used here, another development that came after this was this paper of Eguchi and Kawai, who showed that if you accept these equations, then they can be reduced to a set of equations involving finitely many edges only. So you have this lattice gauge theory on infinitely many edges on the lattice, but somehow you can reduce it to a system with finitely many edges, which is basically random matrix theory with finitely many matrices. So there were some problems. So this Eguchi-Kawai reduction is not, presently it's not thought to be correct. So what they do is they have a modified system of equations called the twisted Eguchi-Kawai equations, and that's what the physicists work with. This was really something that was not, it was kind of suspect, at least from a mathematical point of view. Now, the nice thing about this is that these equations should hold in any dimension. Okay, so on the rigorous side, in 2 dimensions, these can be formulated and proved rigorously in a continuum setting.
Sorry, Sourav, can you say again what's wrong with those on this slide? This.
So Eguchi and Kawai had a reduction to a system of equations involving finitely many edges, but this is what I hear. Of course I cannot read these papers, but this is what I hear is that this is not thought to be correct. So they have a modification. So there was a modification which are known as twisted Eguchi-Kawai equations, and those are the ones that are thought to be.
You say there are also problems with the original Makienko-Migdal equation?
The reduction, the reduction was based on the original equation. So if there are problems with this, so there may be problems with the original ones. So I'm not sure. So the original ones. Yeah, so I'm not sure about that, but
this is essentially what you prove is these.
No, so I don't. So the original forms I don't prove, because the thing is, so this is what they represent, that the expectation of Wilson loop as a polynomial in several other Wilson loops, and this is not what I proved. So this is, this is probably this is not correct. So what I prove is a more complicated system. So I'll tell you. So basically, you can get the recursion in terms of not an expectation of a Wilson loop variable, but an expectation of products of Wilson loop variables. So if you take those as your basic objects, then you can obtain a rigorously derived reduction. So if your basic objects are just expectations of Wilson loop variables, then then I don't know of a rigorous valid set of equations. So I'll come to that.
So just to clarify, so you do know that they are wrong as originally stated?
Well, yeah, I think that's right. Well, if you take n to infinity, they may be correct. So if you let n go to infinity, they may be correct. But certainly, for finite n systems, those are not okay. So in 2 dimensions, these master loop equations were formulated and rigorously proved. This was done by Thierry Lévy, and there is a more recent, cleaner or shorter proof by Driver, Hall, and Kemp. In 3 and higher dimensions, there is nothing in the continuum setting because we don't know how to take the continuum limit. There is only in the lattice setting. And I think this was the first rigorous derivation that I did in 2015 for SON lattice gauge theory. And this is for the equations themselves hold for any beta. Okay, so it's only when you try to take some n going to infinity limit that you run into problems. But the basic equations themselves hold for any beta and any n, okay, and any dimension. Okay. So we will describe these equations now. So as I told Scott just now, that the basic objects are not Wilson loop expectations, but expectations of products of Wilson loops. Okay, so these are the basic objects for this system of equations. And the factorization answers is not assumed; it's actually proved. So it follows from the solution. So I'm able to solve these equations when beta is sufficiently small. So not only are the equations stated, but they're also solved when beta is sufficiently small. And when beta is sufficiently small, I can show as n goes to infinity, you have the factorization answers is actually true. So in language of free probability, there is asymptotic freedom. So that's basically what that means. Okay. So okay, so the statement itself requires some preparation. Okay, so it's not easy to state these equations. The first step is the definition of a string theory on the lattice. So what is a string theory? So in physics, a string theory prescribes an action for a trajectory of collection of closed loops instead of collection of particles. So in Newtonian or Lagrangian mechanics, you have a collection of particles and they evolve in time, and this evolution is written down as a trajectory in a higher dimensional space. And then you describe the action of a trajectory. In string theory, the particles are replaced by strings, okay, just loops. And so you have a collection of closed loops, and they evolve, and the loops can merge and so on. So they trace out a surface, and the surface can have handles and all kinds of things. And then you describe the action of the trajectory. Okay, so that's what is done in string theory. So for the lattice, a string, we will take a finite collection of closed loops in the lattice. Okay, so we'll not take any continuum limits. So we'll just fix the lattice. And then the string evolves over time. These closed loops evolve over time. They can merge, so the number of loops may increase or decrease. Some loops may vanish. Okay, so there are several steps, several kinds of things that can happen. So at each time step, a component loop, so one of the loops may become slightly deformed, so I'll describe what this is, or 2 loops may merge, or a loop may split into 2, or a loop may twist at a bottleneck, or nothing may happen. So this is how, this is a list of all things, and then I'll describe what exactly these operations are. So these are the operations that can happen in this string theory. Okay. And each operation has 2 subtypes. So there is a positive and negative deformation. There's a positive and negative mergers, positive negative splittings, and twistings. Okay, so I'll just describe these pictorially. So I'll just draw some pictures and describe them without going into the details. So here is, for example, a positive merger. So you have 2 loops like this, and this is the same edge E. So they're passing through the same edge. Now, when you merge these 2 loops in a positive way, what this means is that you get this loop. So it goes like this, but instead of continuing this way, it continues the other way, and then goes back and comes like this. So this is merging 2 loops without deleting an edge. That's why I call it a positive merger. Similarly, negative merger is the same situation, but you merge them in a different way so that this loop is this edge is now deleted. So what you do is you go along this loop. Now you reverse the direction. So instead of going this way, you now go this way and then come back and then do like. So again, we are merging. So there are 2 kinds of merging. So either preserving the edge, going over it twice, or deleting that. Okay. Now deformation is basically merging, but with a single plaquette. So you have a single plaquette, and then you throw in the single placket in the loop. So you have the single loop, and the deformation add a placket is just adding a placket to the loop. And negative deformation is kind of you delete the placket. So you have this loop and you delete just one placket. Okay, so that's a negative deformation. So basically, deformation is merger with a single placket. So the difference is that in merger you have two components which merge into one. In deformation you have just one component, and then you are just adding or deleting a placket. Okay, and then you have similarly you have splitting, which is kind of the opposite of merging. So you have this, and then you get back this. So this is like if you go in the reverse direction, that would be a positive merger, and you go in this direction, so that's a positive splitting. So it's just the reverse operation. And negative splitting is like this. So negative splitting is you just break it up with deleting an edge. So you see the positive splitting was you break up one loop into two without deleting an edge. That can happen if you pass over an edge twice in the same direction. And negative splitting happens when you pass over an edge twice in opposite directions. Okay. And then twisting is a little more complicated. So you go over this edge twice, and you do this. Now you kind of twist this around. So I'll not go into the details. And then you have negative twisting, which I'll not go into the details. So you have these operations. Okay. So anyway, so you have these 8 kinds of operations, and you get from any string you do one of these 8 operations. It may yield a string S prime, and this is I denote these sets, so D plus D minus, S plus S minus, M plus M minus, D plus D minus, as deformation, splitting, merger, twisting of 2 kinds. Now the question is, what is the action in our string theory? So in the string theory, you have the strings evolving according to these rules, and so of course you want an action. So you have so you don't have to remember all these things. Yes.
The space. So it's a family of loop. You have no constraint of they can overlap.
No constraint.
You have no constraint.
No constraint.
And the loop can also come back many times.
Yeah, sure. It can pass over an edge several times. It can.
You have local finiteness. You throw an edge on infinitely many loops. So.
Well, the loops are all finite. So it's a finite collection of loops of finite length on the lattice. Yeah. Okay. So here is the master loop equation. Okay. So consider SON lattice gauge theory on ZD for any n and any d and any beta. And let's say string S is a collection of loops L1 to Ln, and define phi S as the expectation of the product of these Wilson loop variables normalized by n to the little n. So this big N is the size of the matrices, and little n is the number of loops. And let S with the 2 bars be the total number of edges in this string, which means the total number of edges that you're traversing. So if you traverse, anyway. So then this phi S satisfies these recursive equations in terms of a linear combination of phi at all these twists and splits and mergers and deformations. So it's a linear system. So the original Macienko-Migdal equations had this expectations of Wilson loops, which the recursive equation was a polynomial in terms of the other things on the right hand side, but with this unproved factorization ansatz, and as n goes to infinity. And this one is a linear system. It's in the language of PDs, is a linearization of the original system in some sense, and it's for finite n, and it holds for any beta. Okay.
This is the Wilson action, or when you say
This is the Wilson action. Yes. Wilson.
SON rather than SUN is the.
Yeah, so that's I'm going to state that as an open problem. So my student Jafarov, he worked out the theory, the similar thing for SUN, and it's somewhat different. The operations are somewhat different. So there should be some kind of unified, equations that hold for any Lie group, but we don't know exactly what they are. So this is specifically for SON. That's what the things work out to be. So I don't know. And the thing has been worked out for SUN also, but I don't know what's the general picture.
When n goes to infinity, what happens?
Yeah, when n goes to infinity, you can, so that I'm going to talk about that a little later, but when n goes to infinity, you should not put beta, you should replace beta by n beta, so that's the 2th scaling. And when you replace beta by n beta, and then you divide throughout by n, some terms are going to go away. So these two twisting terms are going to go away, the mergers are going to go away, but these will remain, so the deformations will remain and splittings will remain, and you get a limiting system of equations, which is simpler. Okay.
So do you prove this by integration by parts, or is it an expansion in characters or something?
So, everything in analysis is integration by parts. So somehow, in that sense, it's all integration by parts. So, so I'm going to tell you how. Yeah, it's integration by parts. Okay. Okay, so I'm going to show you the proof now. So, the Stein equation, that's what we learn when you learn Stein's method. So you have this integration by parts for Gaussian variables. That's what you start with, okay? It's known by various other names, but, Stein has as much of a claim to that as any of these other people. So the following theorem generalizes this to SON. It's a simple result. So consider SON as embedded in R n cross n by n real matrices. So consider this a submanifold of this in extrinsic coordinates. And so suppose f and g are C2 function in a neighborhood of SON in this larger manifold. Okay. So these are functions. Consider this as function on the set of matrices instead of on SON. So it's an open neighborhood of SON. And let E denote expectation with respect to Haar measure. Then you have this system of equations. So expectation of summation xi k del f del xi k g times g is whatever you express this as some system. Okay, and it may look a bit messy, but it's actually quite nice. So this is just integration by parts identity on SON. So if you define appropriately the Laplacian and the gradient on this manifold, so this is now in intrinsic coordinates. So if you define the Laplacian and the gradient on this manifold, and you have this integration by parts identity, and eta is a normalized Haar measure, then if you write the system in extrinsic coordinates, considering SON as a submanifold of matrices, you get back those equations that I wrote down. Okay. And this was actually pointed out to me by Thierry Lévy. So I had the original equations derived by some brute force, and that's my favorite technique. Saves a lot of time. So yeah, but Lévy, he's a very elegant French mathematician. So he looked at this; it was unacceptable to him. So you have this nice system. Now the thing is, the extrinsic coordinates is really important actually. So we will actually have to do calculations, right? So it's yeah. Okay. So let's see how you do the calculations with this. So let L be a loop and E be an edge of L, and let consider the matrix element attached to this edge, and denote the ijth element by Qij. Let M be the number of occurrences of E and E inverse in this loop. So L can pass through E in both directions several times. So you count the total number of times it passes through this edge in either direction. Okay. So it's not hard to show that M times the Wilson loop variable is summation Qij del WL del Qij. And why is this true? It's because WL is a homogeneous polynomial of degree m in this Qij. So if you actually write down down WL, which is a trace of a product of matrices, it's a polynomial in all these matrix entries. And if you fix all other matrices and just consider as a function of Qij's, this single matrix, it's a homogeneous polynomial of degree m because the thing is passing through this edge m times in either direction. So in the U inverse is just U transpose because this is SON. So therefore, it's a homogeneous polynomial of degree m, and if you have homogeneous polynomial, you always have this identity that summation xi del p del xi is m times the polynomial itself. Okay, so that's the very simple reason why you get this identity. Okay, now once you have this identity, what you do is the following. You let S be a string collection of loops. Take any edge in the first loop, okay? Let M be the number of occurrences of E and E inverse in this L1. And let the ijth element of UE be denoted by Qij. Now let G, okay, let G, so you have these two functions f and g in this tiny equation that I showed. Let G be the product of WL2, WL3 up to WLN with the probability density of SON lattice gauge theory. So you take these Wilson loop variables as functions of the matrices, and you take the product of those, this whole thing with the probability density of SON lattice gauge theory, okay? So that's a complicated object. And then m times this Wilson loop product of expectation of a product of Wilson loops is just m times expectation of WL1G. So where this is the product with respect to Haar measure, and this is the product, this is the expectation with respect to Haar measure, and this denotes expectation in lattice gauge theory. Okay, so this is just rewriting this expectation because I've thrown in the probability density into this G. Okay, and then you do this homogeneous polynomial trick. You write WL1 times m as this, and now you're in the setting of the Stein equation that I showed. Okay, and so you really have to work this out. Okay, so you remember the Stein equation, and remember the probability density of the Haar measure and the Wilson loop expectation. So it's some extremely messy thing that you have. Now, somewhat miraculously, this result is an expectation, comes as the expected value of a sum of products of Wilson loops. Okay, there is, there must be some reason why that happens, but I don't know the reason. There is no simple way to see that should be the case, but you just work it out, and this is what it turns out to be. And then what you do is there is nothing special about this first loop or this chosen edge, so you just take some kind of a weighted average of all these equations that you get over all loops and edges, and then you get the system of equations. Okay. Okay. And all these operations, these twistings, mergers, splittings, deformations, everything falls out of these calculations. Yes.
So the WL1, that's sampled from Haar measure, and G is sampled from the SON, the lattice gauge.
No. So consider WL1, WL2, WLN, all these as functions of the just as functions. Okay. So these are all functions, and the probability density of SON lattice gauge theory is also a function. So when you're computing the expectation under lattice gauge theory of this function, it's the same as the expectation under Haar measure of this other function. Okay.
Oh, as in you. Yeah, okay.
Yeah, you see? So you have one function on this side, function of the matrix entries, and you're taking expectation of that with respect to lattice gauge theory. And that's exactly the same as taking the expectation of this other function, WL1 times G, with respect to the Haar measure. Okay? And then you write down this, this thing as using this homogeneous polynomial trick.
So you're just absorbing the probability density. So in the initial expectation for the lattice gauge theory, you had Haar measure at the end. You're basically just absorbing that into
Yeah. So I'm just transferring the problem from lattice gauge theory to Haar measure. Except that now when you're having this G is a very complicated function, and then if you go back to the equation, you see you have to compute all these things, and G is now a product of Wilson loops with the probability density of lattice gauge theory. So you have to really work this out. Okay, so these 8 string operations that I wrote down, they arise naturally from this calculation. So this is built into this system. And as I said, there seems to be no particular reason why this integration by parts should yield an expression involving the expected values of products of Wilson loops. So it's important to have an intuitive explanation for what's going on. So Jafar worked out this for SUN. However, the string operations are somewhat different for SUN, so you do not get the same operations. And there is a interesting generalization problem here. That is, what's an elegant system for all these this thing for general Lie group. So does this always happen? That I suppose there is no reason why it shouldn't happen. That you take any Lie group, you do the same thing, you get the equations, and it must be an equation involving same things, products of Wilson loops on the right hand side also. But I don't see that. Okay. Any other questions? Okay, so now, okay, the large n limit. So let's talk about that. So you have the equations. Now what do you do with that? Okay, so you have the equation. Yes?
Can you just say a bit more about what type of product of
Product of,
when you say product of Wilson?
yeah, so the kind that I had here, so you see the equations I wrote down here. You see you had the original product of Wilson loops on the left hand side. That's where what you started from, and we do this whole trick, and we get the right hand side, and so you apply this integration by parts, and on the right hand side you get expectation of some function of these matrices, and they again are expectations of products of Wilson loops. Now with this special operation, so you could have potentially gotten any function. I mean any polynomial of this. So why should they be specifically certain products of Wilson loops that come up on the right hand side also? Okay, so that's not entirely clear why that should happen. And also yes, over.
The lengths of the string can increase, right? The long terms.
Yeah, they can increase or decrease. So, so for instance, mergers can increase the length, and also deformations. So deformations particularly can increase the length because you're adding a plaquette. So you can have more edges than before. So you can end up with more edges than before than the original loops. You can end up with more loops. You can
increase the number of terms.
It can increase the number of terms in the product also. Yeah.
When you have the deformation, say you have only a single loop. If you do a deformation in this D, say, the deformation term, does that that's only the one plaquette terms? You don't end up with all loops, basically.
No. So you just have one plaquette. One plaquette. Yeah, you have one plaquette. But for instance, splittings may increase the number of loops in the collection. So you originally started with n loops, you may have n plus 1 loops, or mergers may decrease, and
And you only get those terms when the original loops actually overlap.
Yes. So unless they overlap, then you cannot do mergers. But you can do splittings. Yeah, if they pass over the same edge twice, you can have a splitting. Okay. So now this is the large n limit. So 't Hooft, another Nobel-winning physicist. He pioneered this area of large n theories where you look at SON or SUN with n going to infinity. So this is known as large n gauge theory. And the reason is mainly that it simplifies many calculations. Okay, so that was the program that, so in the original paper I think it said that, you have SU5 theory is important for certain purposes, but 5 is kind of large because 1 over 5 squared is small. So, So I'll talk just a little bit about this, about planar diagrams and their connections with random matrices. So this work is also the root of that, all that work. So planar diagrams, so recall that we had this perturbative calculations in quantum Yang-Mills theories that I described in the first lecture. You don't really have to recall, but just. So it was mentioned that these calculations reduced to Gaussian moment computations, okay, which are handled using Feynman diagrams. So 't Hooft realized that if you take these Feynman diagrams and you slightly modify them, basically you take each line in the Feynman diagram replaced by kind of 2 lines, okay, that's the kind of thing, then you get from diagrams to surfaces, okay, so there is some combinatorial trick by which you get, so we have been seeing a lot of that kind of thing in this conference. You can convert these diagrams to surfaces with these edges, vertices, and faces. And 't Hooft also suggested the parameter beta should be replaced by n beta. So this is known as 't Hooft scaling. Okay. So when you replace beta by n beta and you do this modification, the Feynman diagrams are modified to certain other kinds of diagrams which are surfaces. So this has the interesting effect that when n is taken to infinity, this perturbative series expansion that you get using this technique becomes a series in powers of 1 over n. So this is known as the 1 over n expansion. And moreover, the kth term in the expansion is a sum over surfaces of genus K. Okay, so this is the planar diagram theory. So this was 't Hooft's observation that you have this very interesting thing going on, you can take this Feynman diagram, slightly modify them by replacing single edges by double edges, and then you end up with sum over surfaces, and the expansion, the kth term, is exactly corresponding to sum over surfaces of genus K. Okay. And this has led to a large body of work, so I'll not elaborate on that. And Alice in probability, Alice Guianet and collaborators have worked a lot on these things. But as far as I know, the TÜV's original thing with the lattice gauge theories, this has never been made rigorous. Okay. So now, TÜV's theory is perturbative. So let's look at what happens in non-perturbative setting. Okay. So recall that S is a collection of string is a collection of loops, and then phi n S. So I didn't put the n before, but let's put the n now, because we are going to take n to infinity. And you take this product of Wilson loops, take expectation in lattice gauge theory, divide by n to the little n, just to make it nice. And here the expectation is taken with respect to SON lattice gauge theory on ZD by taking a weak limit. So it's an infinite volume limit. So here you can define lattice gauge theory on ZD. So you just take that, take any weak limit. And like TÜV, let's suppose we replace beta by n beta, okay, and then send n to infinity. So now the question is, does this phi n s this converge to a limit, and if so, can we calculate the limit? Okay, so that's the main objective now. Now the first thing to observe is that these are always bounded by 1, because these are unitary matrices of size n. So the traces of these matrices are always bounded by n. So each of these quantities is bounded by n. Okay. So this numerator is bounded by big N to the little n, and so you're dividing by this. So you're ensuring that these things are always bounded by 1, no matter what. Okay. And there are countably many of these strings. So you can always get a subsequential limit. So even if they don't converge to a limit, you can always get a subsequential limit, and moreover, you can get a subsequential limit that holds simultaneously for all strings by just a diagonal argument. Okay. So now, to show that they converge, you just have to show that this subsequential limit is unique. So that will suffice to prove that you have a limit. So let phi be a subsequential limit of phi n simultaneously for all strings under this TÜV scaling. Then phi satisfies this limiting master loop equation. Okay. So just as I said to Bertrand, that the deformation and splittings are only things that survive. The mergers and twistings go away when you take this limit. Okay. Twists and mergers have disappeared. So this seems like a much nicer system. And again, this holds for any beta. Okay, just like the finite n system, this holds for any beta, except that you don't know whether this subsequential limit is unique. Okay. So you just take any subsequential limit simultaneously for all strings by a diagonal argument, and then you have the system of equations, this limiting system of equations. Okay. And what I hear from the physicist is that understanding this kind of thing is also very important. The large n limit is still considered to be an important object and still not well understood. So you don't really have to prove things for finite n. If you can prove non-trivial results for large n, then going to infinity limit, that's also interesting even from a physical point of view. Okay. So note that this holds for any beta. So if this system of equations has a unique solution, then we may conclude that phi n s converges to phi s as n goes to infinity. So we just have to show that this has a unique solution. Okay. So this is, remember, this is for every string, which means every collection of loops, you have some quantity phi s. So it's a huge system of equations. Okay. And you have to show that this has a unique solution. Okay, so how do you do that? So what I showed in this paper is that this is, yes?
You have a sort of a easy intuitive explanation why basically all of those things will survive and why the other operations, local operations?
No, I don't have. Yeah, just from the calculations. That's a very good question. So there must be some reason. Well, no, there is one reason actually. So what happens is that the leading term of this phi s. So phi s, you can well, if you consider phi n s, okay. You can try to write a 1 over n expansion. Phi n s is phi s in the first term plus 1 over n times phi, some other term plus so on. So just like in the TÜV expansion, the first term should involve only surfaces of genus 0. So surfaces meaning, you know, when the strings evolve, they trace out surfaces. So the first term should involve somehow surface of genus 0, which means that as the strings are evolving, they can only split, they cannot merge back together. Okay, if they merge back together, so actually with Jafar, we have a second paper where we evaluated this full 1/n expansion, and the kth term involves things which have, where the strings are allowed to merge k times, which means you can have surfaces of genus k. Now, I don't know, so that kind of explains why the mergers are not allowed, but I don't know about twisting. So, you know, what are twistings doing? You know, the twistings seem to have no continuous analog somehow. You know, I don't quite understand what is going on for that. Yes.
I mean, and there's no way to represent your things by forgetting out the orientations of the loop and sort of have a version where you...
I don't know. There may be, but I don't know. So again, you know, that's also a good question, because you know, it would be much nicer. You know, that's again what the physicists and the mathematical physicists, they tell me, is that it would be much nicer if this. So I'll tell you the actions of these trajectories. The actions really depend on how the strings evolve, but it would be nicer if the actions can be described just as a function of the surfaces that are traced out by the strings. So I don't know how to do that. So I showed that the system has a unique solution when beta is sufficiently small. And this shows this, and there is this open problem. So show that the limit exists for any beta, not only beta small. You know, I don't see any reason why it shouldn't exist for large beta. You know, so that's a valid argument in physics. You know, I don't see any reason why it shouldn't happen. So actually, so somehow I don't see any reason why it shouldn't happen that the limit exists. Yes.
You know that for large beta there is no unique solution, or you just know how. You don't know.
For large beta, I don't know there is no unique solution. So you know, I don't know anything. I mean, so of course you can have subsequential limits and the master loop equations will hold, but the existence of the limit is same as saying that the system has a unique solution. Well, no, you're right. So that's not quite correct.
I was asking about exactly distinguishing.
Yeah. No. You're right. Yeah.
So when you say beta is small, how do you say what does it mean small?
Beta small just means that beta is less than a constant. That just depends on the dimension. Okay, because we are fixing the lattice gauge theory here, n going to infinity, and we have the 2th scaling n beta. So now I'm just saying beta is smaller than some positive constant that just depends on the dimension of the lattice. And that's all. Yeah, no, that you're right. So right. Yeah, so it is at least theoretically possible that there may be multiple solutions, but
you would expect a unique solution, actually.
I would expect a unique solution, I think. Yeah. Well, there is a boundary condition, which is that phi of an empty string is 1. Okay, so with that boundary condition, so you can have an empty string which has nothing, no loops. So by the usual convention that the empty product is 1. You have that with that boundary condition. So here's a sketch of the proof of the uniqueness. So let phi and psi be 2 solutions, and let delta be the set of all finite sequences of integers. And if you have 2 such sequences, we say that delta less than delta prime if the 2 sequences have the same length and delta prime dominates delta in each component. Suppose you say that. Now you take a string S and let delta S be the lengths of these components. So this gives you a mapping from set of strings into this big delta. And then for any finite sequence of integers, little delta, you define d delta as a supremum over absolute phi s minus psi s over all strings whose delta sequence, whose length sequence is dominated by delta. Okay, you define this. And then for any sequence of finite integers, you define an index iota of delta as a sum of the deltas minus n. Okay, so defined like this. And then for lambda belonging to the interval 0, 1, lambda strictly less than 1, you define f lambda as sum over all possible delta, all finite sequence of integers, lambda to the power of this index times this difference d delta. Okay, so you define this. Okay, so this index will be important later also, but is this definition clear? So we're just starting with phi and psi be two solutions of the master loop equations. Okay, so now we define f lambda this function. So the first thing to show is that f lambda is finite if lambda is sufficiently small. So this is not very hard because d delta is bounded by 2 always, because these are bounded by 1. So d delta is always bounded by 2. So it just reduces to a counting argument. So how many sequences can there be which have some value of this, and then you try to sum, and then you show that if lambda is small enough, depending on the dimension, then this is finite, okay? Because lambda is less than 1, so Now, then what you do is you apply the master loop equation. So you see that, you see that phi and psi both satisfy the master loop equation. So when you take this d delta, here you can substitute the right hand side of the master loop equations, okay? The limiting master loop equations, and then you work through that, and somehow you end up with this inequality. Just as an application of the master loop equations, you end up with this inequality. And the master loop equations only have splittings and deformations, so that's very important. If you had mergers, you wouldn't get an equality like this. So you only have splittings and deformations which allow you to do this. And what splittings do is that they reduce this index, so that's very important in the next slide. So, okay. So you have this equation, and now it's very simple. So now what you do is that suppose you choose lambda to be sufficiently small, and then you choose beta depending on lambda and the dimension to be sufficiently small, then this part becomes strictly less than 1, which means that f lambda must be 0. And once f lambda is 0, it implies that d delta is 0 for all delta, and therefore phi is equal to psi. Okay. So this is So this is the proof of the uniqueness. Okay, so so you have this. Okay, so before I move on, so I'll just give you something about quantum gravity. But any questions about this proof? Yes.
So you don't know uniqueness of the solutions to these equations at finite n.
No, n going to infinity. This is infinite limit. So uniqueness of the limiting system. Yeah. So for the finite n, I don't know. Finite n, I don't know the uniqueness. No. So I suppose similar things may go on. Yeah, we had to deal with some aspects of finite n for the full 1 over n expansion. But yeah, really, I mean, the answer to your question is no, I don't know. Okay, so the next thing is, okay, so you know that there is a unique solution. Now, what is the solution? Okay, so for that, let me discuss a little bit about quantum gravity, which the phrase you have heard in this series of lectures, in this conference many times. But let me give you some background. So there is no quantum theory of gravity, and the physicists all want this. Now, the quantum effects are very important at small distances where gravity has no effect. Okay. On the other hand, gravity is felt at large distances where quantum effects are negligible. So see, this unification is, the question is whether this is really necessary, except from an academic point of view that you really want a unified theory, but it's not just an academic goal. The thing is, in objects like black holes, you have both gravity and quantum effects. Okay, so that is one big reason why people want to study quantum gravity, because in black holes, you have black holes are quantum mechanical. Quantum effects are very prevalent in black holes, as well as gravity is very prevalent. So this is one reason why people want to study quantum gravity. Okay. So now, in classical physics, you have particles moving along deterministic trajectories. In quantum physics, trajectories are probabilistic, although these are complex probability amplitudes, but these are essentially probabilistic. So now general relativity is a classical theory in the sense that the curved spacetime that you have in general relativity is deterministic. Okay. So now when you try to do a quantization of that, you would have to replace this deterministic curved spacetime by randomly fluctuating spacetime. Okay. And that's why you get these random surfaces. Why these are called quantum gravity. If you go back and you have to call your mom and say, I was at this lecture in a conference about quantum gravity. What's quantum gravity? You can tell them that's random fluctuating space-time. Okay, so so the most promising approach is string theory. So roughly speaking, you have strings moving randomly, trace out random surfaces, and that's where the random surfaces come from. And if you have higher dimensional strings known as branes, they trace out higher dimensional random manifolds. Okay, so that's where all this study of random surfaces or more generally random manifolds come in. Now there is this thing called gauge string duality. So there is a theoretical result of Weinberg and Witten, theoretical physics result, that it's impossible to generate gravity using quantum field theories in the traditional sense. So I cannot go into the details of that. But there is this, so you have this quantum field theories that explain, strong force, weak force, electromagnetic force, but they show that you cannot just, explain gravity using that. So there is an impossibility result. Okay. However, they have this unstated assumption that one is looking for both theories in the same dimension. Okay. So if you throw away that assumption, then it was observed by Maldacena that you can have quantum field theories that are dual to string theories in one dimension higher. Okay. So duality here means that any calculation that in one theory corresponds to some calculation in the other theory, and they have this whole list of calculations that they have one calculation in quantum field theory, you can do the same calculation by some other means in the string theory, in the gravity theory. Okay. So this is known as the ADS-CFT duality. This is anti-de Sitter gravity, and CFT is conformal field theory. So that's n equals 4 supersymmetric Yang-Mills theory. And this is called the gauge string principle. And the principle of going to one dimension higher is known as the holographic principle. Okay. Just some terminology if you hear these things. So this gauge string duality were already present in the Stoops planar diagram theory, because you have this sum of the surfaces, which are kind of random surfaces, and you have this lattice gauge theory on the one hand. Although these surfaces are kind of not real physical objects, they're like Feynman diagrams made into surfaces. Okay, so that was not completely clear how that corresponds to gravity. So this duality between SO and lattice gauge theory for large N and lattice string theory, this was in this paper. This may be the, I have been talking to people for the last 3 years, this may be the first rigorously derived gauge string duality result. So, because as I said, Tufts results have not been made rigorous. I'll now describe this result. Okay, so this is a solution. So first I have the equations, then I have the existence of the solution, existence and uniqueness of the solution for small beta, and then what is the solution. So in the lattice string theory that I described, call the trajectory vanishing if it vanishes after a finite number of steps. So you can have strings reducing, right, in this with deformations, and they may eventually vanish. So if you reduce to a single plaquette, and if you deform it negatively with the same plaquette, you'd get nothing. Okay, so things may become nothing. So call the trajectory vanishing if it vanishes after a finite number of steps. So let X be S0, S1 up to Sk be a vanishing trajectory. So S0 is the first string, first collection of loops. S1 is after one step, and so on. And Sk is finally empty. And the action of this trajectory is defined as a product of the one-step action. So going from S0 to S1, S1 to S2 up to S, where this will be defined in the next slide. So now I have a string theory where we have a sequence, we have a string evolving in time, and we want to describe the action of this trajectory, just like you have the Lagrangian in classical mechanics. And the action is described just like you have in, let's say, in a Markov chain, a product of probabilities, sequential probabilities, you define like this, where this action of subsequent steps is defined as follows. Okay, any questions about this? Okay, so the action is defined like this. So let S be a string, let absolute S be the total number of edges, and then you just have some rule. So as you go from S to S prime, if S prime is a positive or a positive twisting or positive splitting or positive merger, you have this. If it's negative twisting, negative splitting, negative merger, you have this. If it's a positive deformation, you get this, negative deformation. So it's like so this transition weights are like probabilities, except that they can be positive or negative. Okay. And then the action of a vanishing trajectory is computed by multiplying the weights of successive transitions until it vanishes. Okay, so that's how you define the weight of a trajectory of strings. And here is the main result. Consider SO in lattice gauge theorem ZD with coupling parameter n beta. Let S be a string and define phi n s to be this. So then, if beta is small, then the limit exists as we showed before. But moreover, the limit equals the sum over all trajectories starting from this string S. All vanishing trajectories, which consist only of splittings and deformations, no mergers or twistings. And let Wx be the action of this trajectory. And then you sum over all possible trajectories of this action. So this is similar to what arises in this gauge string duality in ADS-CF2 duality. That is, this Wilson loop expectations in the limit large n limit can be expressed as some integral. So they have a continuum setting as an integral of the action over all trajectories. So it also appears in that setting. So it's analogous to that. You have a sum over all vanishing trajectories, and Wx is the action, and moreover, this you can show it's absolutely convergent. So you can this gives an explicit solution, in some sense, of the system of equations, the Mackian-Migdal equations that I wrote down.
Looks like something combinatorial, right?
It is
So
combinatorial.
why would you have then a condition on beta?
Well, first of all, this result is not true for large beta, actually. So why is this not true for large beta? So in 2 dimensions, for instance, if you just go to 2 dimensions, so there is a recent work of Basu and Ganguly where they managed to solve this system in 2 dimensions, explicitly solve this system in 2 dimensions using combinatorial techniques. And this right-hand side, let's say you take a single plaquette. Let's say your string is just a single plaquette. Okay, so this side becomes beta times something, maybe beta or 2 beta, something like that. Something very simple when you have a plaquette. But obviously, that result cannot hold for large beta because the limit has to be bounded between 0 and -1 and 1. Okay, so this result itself cannot be true for large beta. Okay, yes.
I mean, wouldn't it be more natural somehow to interpret the sum of the right by time reversing, by saying, this is something that is created by deformation and actually merging rather than splitting? I mean, things coming from different times, but sort of a tree of stuff.
It may be, yeah, that's probably true. Yeah, that's probably true. So, yeah, I don't have it in that form, but
this large n would mean that it's, when you come twice back, then you're unlikely to be able to split whether merging is actually possible with each other.
yeah, that's possibly true. Yeah. So I don't have it in this form, and so this is what I have, and I would really love it if somebody here can take this further in 3 and higher dimensions. Get something more out of this expression. So as I said, in 2 dimensions, Basu and Ganguly have been able to explicitly solve this using combinatorial techniques. But in 3 and higher dimensions, this side looks like something which may be manageable, but hasn't been done yet. So can you actually solve this recursion and get more information out of this? So in the paper I used this for a bunch of things. So I used it to prove the area law at small beta, and I used this representation to prove factorization, the factorization ansatz, that is the asymptotic freeness. That kind of thing I was able to do using. So this has been used for a few things in the paper, but needs more. So this condition is the trajectories can only have deformation and splittings and no mergers ensure that the surfaces traced out by the trajectories have genus 0 in some sense. And in later work with Jafar, we computed the full 1/n expansion, and the higher order terms involve sums over trajectories of higher genus. Now, the formulas look similar to 2 sum over planar diagrams, but they're actually different in the sense that this is on perturbative expansions in continuum theory, whereas this result is for a non-perturbative theorem for lattice gauge theory. So that's kind of different, although they look similar. It's different. Okay, so here is a little bit of a proof sketch. I have a few minutes. So what you do is, for a string S, define the index of the string as a sum of the lengths of the individual components minus the number of components. Okay, so you define an index. And we proved facts about strings by induction on the index. So the main thing is that when you split, so first of all, you can show that the index is always strictly positive for any non-empty string. It's 0 if the string is empty, but for any non-empty string it's positive. That's easy to show. And the crucial thing is that if S prime is a string, so I used this terminology earlier, sorry. If S prime is a string that is produced by splitting S, then the index decreases. It must decrease, okay? So that's a little lemma that you can prove, and this is crucial for allowing us to do induction. So what you do is you first define a collection of coefficients ak of s for each non-negative integer k and each string s using an inductive definition. So you do induction on k and this index. Okay, suppose you have defined aks for all k less than something and for all s with the index less than something, then you go ahead to do the next step. So this is a two-way induction. Okay, there's a two-way induction on these two things, k and this index, which guarantees these two properties. For beta sufficiently small, this power series converges. And the second thing is that this function satisfies the limiting master loop equations. Okay, so you show these two things, that this inductive definition, which I am not displaying here, ensures that it converges absolutely and this satisfies the limiting master loop equations. And so these two properties and uniqueness of solution will show that phi n will actually converge to this limit, where this limit is given by this. Okay.
Does the radius of convergence of the series in beta depends on S?
No, it doesn't. So it doesn't. So something depending on the dimension, but I don't remember. So yeah, that's a good question. That is, this is converges, but it does not depend on beta, the radius of convergence, right? Okay. So now then, for each k and for each string s, let xks be the set of all vanishing trajectories with only deformations splitting the start and s of exactly k deformations. And then you again show by induction, so this is again by induction on k and s using this index, that this quantity aks times beta to the k is exactly the sum of these weights of, so this is again shown by induction. And once you have this, you get this, this result, combining these two steps. That's a very high-level sketch of the proof. And this absolute convergence requires a different argument. Okay. So there are all kinds of things involved. You have combinatorial, Catalan numbers get involved, and all kinds of things. But this is from a very high level. Okay. So finally, to finish, there are open problems. So develop a continuum version of these results, or at least for some large beta. And as I said, that there has been some progress in 2 dimensions using this combinatorial connections and free probability. So can this be extended to higher dimensions? And as before, even establishing the existence of a limit would be a significant thing. And so finally, so this is it's not just so mathematicians, really sometimes it's strange what they're working for. But this is actually important for some things. So, okay, thank you.
So I guess one thing I didn't quite understand was, so you have this lattice gauge theory and you have these Wilson loop variables, you wanted to calculate expectations over these, and then you show you can do some sorts of operations on these loops to reduce this to certain other computations within the same lattice gauge theory. But in what sense is this a string theory?
In the sense that you have this evolving strings. I mean,
in what sense are they evolving?
Using these rules, so you have these strings and then they evolve. They can split or merge or deform, and they.
But is there like? So can you write down like could you write down like, how do I say this properly? Can you formulate this as a sort of an actual dynamics type quantum field theory type thing?
Well, I mean, it's
in the same way that you like integrate over.
Yeah, no. So there is no. Okay, so if you're asking whether there is some existing physical model to which this connects, I don't know of that. Whether like that's one of the things in ADS CFT theory, that you have this duality, and on both sides you have some familiar object. So on the gauge theory side, you have this CFT conformal field theory, which is a familiar object. On the right side, you have on the gravity side, you have this ADS theory, which is also kind of a familiar object. I mean, these are all. I should mention these are all toy models which have nothing to do with reality, but you have this anti-de Sitter gravity, which is also, and these two are connected. So here on the one side you have this lattice gauge theory, which is a very concrete, well-known model for something concrete. But on the right-hand side you have this string theory, which is which emerges naturally from the calculations, but it doesn't correspond to any string theory that's known and has been analyzed.
Is it a string theory in the sense that you could write down like a Lagrange for this and like actually in the same way? Could you write this down in such a way that it looked like the lattice gauge theory? Because you have an e to the minus beta something.
Yeah, I wrote down the action.
Maybe, I must have missed that at the beginning of the.
Oh, I wrote down the action of the string theory. This Wx that I wrote down.
So if that's the action, you can presumably write down.
Yeah, so this is the action of a trajectory as a product of individual steps, and individual steps are defined like this.
Do you still like do you integrate over time this particular thing with some?
Well, integrating.
Can you write this out as like a path integral? Effectively?
Yeah, so I'm taking a product. So if you take the log of this, it's e to the power the sum of the logs. Okay, so in that sense, it's e to the power of an integral. Yeah.
Okay.
The action. Yeah. Yes, Nathan.
When you move to SUN, so can you say just a few words about sort of you're just going to change slightly the?
Yeah, so there are some other operations. I don't exactly remember what Jafar got, but he got some other operations. Not just twistings and mergers. So he and splittings and deformations. He got some other operations.
Orienting the additional thing that will correspond to sort of.
Something like that. I don't exactly remember what he got. So, yes.
Do you know how to express the Schwinger-Dyson equation for SUN in terms of like gradient and Laplacian, like relativity?
Yeah. So that's also in Jafar's paper. So if you look on the web,
You can also
do
in a
that.
nicer way.
You can do that.
Yeah, so just one thing, you mentioned that it's possible to take a local limit, from the finite box to ZD. Is that clear that this can always be done independently of beta, or does that also depend on beta being small?
No. So you can always do that, but whether this infinite volume limit is unique depends on beta. But the existence is always there because you always have compactness. And in general, statistical mechanics, the existence of the infinite volume limit is not a big question. So you can.
If you don't have a uniqueness of this local limits, how can you hope for there to be uniqueness of the solution?
If you don't have uniqueness of the local limit, that's right. So yeah, but you can have non-uniqueness for small finite n, but you can still have uniqueness for large n. That can happen. Then going to infinity limit, you can still have uniqueness.
Yeah. Has anything been done with lattice gauge theories where you have a finite group instead of a big group?
Yes. So there is some work on finite abelian groups, I think by Christian Borgs before he turned into a different kind of mathematician. So he has worked on finite abelian groups. You can do this character expansion and that kind of thing with finite abelian groups. For finite non-abelian groups, I don't know so much that has been done. Yeah, that's a good question. Although the physicists keep saying that you see all the gauge theoretic features only when you have continuous symmetries. Yeah, and I have some unpublished results, or that'll be lost if my computer crashes. But there are some things, but yeah, not much.
No more questions? We can thank Sourav again.